the Entropy. Good day. So today we are from group Entrepreneur are going to present about we are choosing topic 12, which is entropy. So the group members are Ridwan bin Nordin, Alif Ikram bin Nur Tamizi, Ashraf Muazzam bin Muazzam, Ahmad Ashai Fitri bin Shahrin, and Aiman Hakimi bin Amir Hatta. So my part is I am going to present about the introduction of the entropy. So as we can see from the slide, entropy is the measure of a system's thermal energy per unit temperature that is unable for doing useful work. Because work is obtained from ordered molecular motion, the amount of entropy is also a measure of the molecular disorder or randomness of a system. So the concept of entropy provides deep insight into the direction of spontaneous change for many everyday phenomena. In this topic, to provide a quantitative measure for the direction of spontaneous change, we are using Clausius introduced the concept of entropy as a precise way of expressing the second law of thermodynamics. The Clausius form of the second law states that spontaneous change for an irreversible process is an isolated system always proceeds in the direction of increasing of entropy. Besides that, in the topic of entropy, there is another subunit or subtopic we are going to present, which is the isotopic efficiency. Isotopic efficiency is a parameter to measure the degree of degradation of energy in a steady flow devices. The ideal process that can be served as a suitable model for adiabatic steady flow devices is the entropic process. Another one is the entropy balance. For entropy balance is an expression of the second law of thermodynamics that is particularly convenient for thermodynamics analysis. The objectives of our experiment or our project is to examine a special class of idealization process called isentropic process, to develop the property relations for this isentropic process, and to derive the reversible steady flow work relations. Next, we have to develop the isentropic efficiencies for various steady flow devices. Lastly, we are going to introduce and apply the entropy balance to various systems, since our topic covers two parts, which is isentropic efficiencies of steady flow devices and also entropy balance. That's all from me. I'm going to pass to the next presenter.
I will continue about calculation. So question one is the situation that illustrate the concept of entropy. So the example below will serve the illustrate how the entropy change in a reaction can be predicted. So the first chemical reaction is Cl2 gas become to Cl2 liquid. The entropy is decreasing because gas is becoming a liquid. Then second reaction is CaCO3 solid become to CO solid plus CO2 gas. The entropy is increasing because a gas is being produced and the number of molecule is increasing. Next reaction is N2 gas plus 3H2 gas become to 2NH3 gas. The entropy is decreasing because four total reactant molecules are forming two total product molecules. All are gases. Then next reaction AgNO3 plus NaCl become to NaNO3 plus AgCl. The entropy is decreasing because a solid is formed from aqueous reactant. So next, H2 gas plus H2 gas become to 2HCl gas. The entropy is change is unknown, but likely not zero because there are equal number of molecules on both sides of the equation and all the gases. Okay, next, this is question 2. Perform change in entropy calculation involving standard entropy. So the knowledge of the entropy of substance allow us to calculate the entropy change for a reaction. For example, the entropy change for the vaporization of water can be found as follows. So this is the reaction. Delta S equal to S H2O gas minus S uh, H2O liquid. So we uh, calculate the reaction, then we get 118.8 joule joule Kelvin point mole. So the entropy change for the vaporization of water is possible because the gas state has higher entropy than the liquid state. In general, the entropy change for a reaction can be determined if the standard entropy of each substance are known. The equation below can be applied like the equation below. So next question. Okay, we continue. The standard entropy change is equal to sum of all standard entropy of the products minus the sum of all the standard entropy of the reactant. The symbol N signifies that each entropy must first be multiplied by its coefficient in the balance equation. The entropy change for the formation of liquid water from gases, hydrogen, and oxygen can be calculated using this equation. So from the reaction, we use the equation. Uh, then we calculate until we get negative 327 joule Kelvin mole. The entropy change for this reaction is highly negative because three gases molecules are being converted into two liquid molecules. According to the drive toward higher entropy, the formation of water from hydrogen and oxygen and unvariable reaction. In this case, the reaction is highly exothermic, and the drive toward a decrease in energy allow the reaction to occur. Okay, next.
For question 3, we need to find the isentropic turbine efficiency. As provided with the turbine below, we know that the turbine is a steady state and the air is an ideal, and we should ignore the kinetic and potential effects. Now to find the isentropic efficiency, we should use the formula WCV over m, and with the same with the same but different denominator. To find the WCV over M, we need to use the formula H1 minus H25. Now, H1, we are given the amount, the value, which is 498 kilojoules per kilogram. But for the denominator, but for the H25, we need to use the formula P2, pressure P2 over P1 equals to PR2 or PR1. Now, we could to find for value P1 and P2, we know the value is 5.0 bar and 3.45 bar, and for the value of PR1, we know that it is 3.806, but for PR2, we do not know the value. To find the PR2, we need to substitute the value, and we get the value is 2.626. Now all we need to do right now is just substitute the value into the formula to find the H25, which is WCV over M equals to 498 kilojoules per kilogram minus by 360 kilojoules per kilogram. Thus, we find the denominator. After that, we could finally find the turbine efficiency by dividing the 30.3 kilojoules per kilogram divided by 40.4 kilojoules per kilogram. Thus, the isentropic turbine efficiency is 0.75%. Next question. For question 4, we are given an isentropic expansion on a helium in a gas turbine. In this turbine, the high pressure stage receives a gas of 0.3 at this figure, P3 equals to 6.7 MPa, and from a heat exchange and exhaust in another heat exchanger. Now, what this question want is to determine the work done by this turbine and calculate the real temperature at the exit of the turbine when the isentropic turbine efficiency is at 0.91, which is 91%. Now, from the first law of thermodynamics, we know that the work done by the turbine is an isentropic process, thus can be calculated from Wt equals to H3 minus H4s equals to Wts equals to Cp times by T3 minus T4s. Now, from ideal gas law, we know that the molar specific heat of an monatomic ideal gas is Cv equals to 3 divided by 2R, which is equals to 12.5 joules per mole K, and Cp equals to Cv plus R equals to 5 over 2R, equals which means the value is 20.8 joule per mole K. Now we transfer the specific heat capacities into units of joule kilogram via Cp equals to Cp times by 1 molar weight of helium. Thus we get a value of 5,200 joules per kilogram. Now the work done by gas turbine in isentropic process is then with the formula of Wts equals to Cp times by T3 minus T4s times by the isentropic, which equals to 5,200 times by 1190 minus 839, which bring the value of 1.825 mJ per kilogram. With this, we use the find the Wt real equals which use the formula of Cp times by T3 minus T4s times by the isentropic efficiency, which equals to 1.661 mJ per kilogram. Next, for question 5, we use the closed. For question 5, it asks for the closed system entropy balance, which is a 1/2 kilogram of propane initially at 4 bar 30 Celsius, which equals to 303 Kelvin, undergoes a process for 14 bar 100 Celsius, which is the 373 Kelvin, while being rapidly compressed in a piston cylinder assembly. Heat transfer with surrounding of 900 Celsius occurs through a thin wall. The net work is measured at 72.5 kilojoule. Kinetic and potential energy effect can be ignored. The question asks us to determine whether it is possible for the work measurement to be correct. Now, for this question, we use the formula for S2 minus S1 equals to the integral of SQ per T plus sigma. We also use the formula of different energy equals to Q minus work. So we use that. For this question, we do not know the energy, the initial and the exit energy. Thus, we need to refer to the properties table. Given that the propane is initially at 4 bar 303 Kelvin, and after the process it is 14 bar 373 Kelvin. Now, referring to the properties table, we know that the initial energy is 472.2, while the exit energy is 577.9. With this value, we could use the second formula to get 0.5, which is the mass, times by the initial and exit energy minus the initial energy equals to Q minus the network. Now we get the value of Q, which is negative 19.65 kilojoule. Then we use the first formula to find the sigma value, using 0.5 the mass times by 2.092 minus 1.969 equals to the value of SQ over T, which is negative 19.65, as we get the value of Q before, divided by T 293 plus sigma. Now, just basic addition and subtraction, we can get the value of sigma, which is 0.129 kilojoule per Kelvin. Now, given that 0.129 kilojoule is more than 0, thus the work measurement seems to be correct. So we can assure that this is correct. Thank you.
And today I will continue for the question 6. For the question is find the entropy for the system. Right, we have two container here. So the first container have temperature 100 Celsius and have mass 250 gram. And for the second container have 0 Celsius and have same mass like first container, which is 250 kilogram. First of all, we need to find entropy for the first system, which is container 1, which is delta Q over average of temperature, also equal to MC delta T over average temperature. So we just put all the information uh, to the formula, and we will get negative 150.4 joule over Kelvin per Kelvin. Sorry. Okay, for the second container or second entropy, we also use the same formula, MC delta T over average temperature, and we get 175.6 joule per Kelvin. And for the entropy of the system, we just add the two entropy, so we get negative 150.4 plus 175.6, and we get the final answer is 25.2 joule per Kelvin. Next. And for the question seven, a copper block of mass have 1 kilogram and have 500 Kelvin is immersed in lake at 300 Kelvin until it reaches thermal equilibrium with water. So just focus on the data that given, which is isobaric. Uh, sorry. Kejap ah. Isobaric apa namanya? Syah, nak aku sambung dari awal ke Syah? Aku sambung dari awal ya. Tak, maksudnya question 7 je lah. Aku mula dari awal. Okay? Okay, for question 7, a copper block of mass 100 kilogram of mass at 500 Kelvin is immersed in lake at 300 Kelvin until it reaches thermal equilibrium with water. So just focus on the data that given, which is isobaric specific specific heat of copper is 0.38 kilojoule per kilogram Kelvin, and isobaric specific heat of water is 4.287 kilojoule per kilogram Kelvin. So the total transfer to the lake. The question want us to find the heat transfer to the lake, change in entropy of the lake, and change in entropy of the copper. So first, total transfer to the lake, which is Q integrate, which is Q integrate of MC theta. So we get just integrate like usual. So we get the final answer is Q equal to negative 77.2 kilojoule. And change in entropy of lake, use the equation for the entropy, which is Q over T, temperature, and just put the Q, which we already get from the first question, 77.2 over 300, which is lake temperature, and we get 0.257 kilojoule per Kelvin. And change in the entropy of the copper, we need to integrate delta Q and equal to MC differentiate T. Just differentiate like usual, and we get MC, which is isobaric specific heat for copper, ln T, ln T, and just put all the data in the question, and the final we get entropy for the copper block is negative 0.197 kilojoule per Kelvin. We get the final answer is negative because the heat from the copper goes to the water. The copper lost heat. That's why we get negative. Next. For the question 8, air in piston cylinder assembly initial at 4 bar, 6 Kelvin, 600 Kelvin, and the volume at 0.43 meter cubic, expand asymptotically to pressure 1.5 bar. So determine the final temperature and the work. First, we need initial state and the final state. So the initial state pressure that given is 4 bar and temperature also given 600 Kelvin. For the final state, we given pressure is 1.5 bar. So for the volume is 0.43 meter cubic for the initial state. If we see the initial state, we can get the internal energy and also PR using the pressure using the temperature using the temperature from the table. So from the table of ideal gas, properties of ideal gas, we get 434.78 joule for energy and also PR 1.628. PR doesn't have any unit. So using this relativity PR, we can get PR2 for the final state. So we get 6.105. So we can use that information from PR2 to get final temperature and also energy by using the table also. After that, we can calculate work by using the information which is temperature and also the final energy. So the formula for the work is the W per M equal to negative final energy minus first energy, and we will get 107 kilojoule per kilogram. Next. For the question 9, the question asks, the question is, can the entropy of the system during the process decrease? So the total of entropy of the system either increase or remain constant in any process. It will never decrease. For example, heat transfer cannot occur spontaneously from cold to hot because entropy will decrease. Entropy is very different from energy. Entropy is not conserved but increase in all real process. Okay, dah habis dah.
Okay, we continue to the question 10. Entropy change at transition temperature. Ice to water or water to vapor and reverse. At the temperature at which the change of state occur. The two states are in equilibrium with one another. For an ice to water system, equilibrium takes place at 0 degrees Celsius. So delta G is equal to 0 at that temperature. The heat of fusion of water is known to be equal to 6.01 kilojoule per mole. And so the Gibbs free energy equation can be solved for the entropy change that occurs during the melting of ice. The symbol delta S FUS first represent the entropy change during the melting process, while TF is freezing point of water. So we can use the equation of delta G equal to 0 and equal to delta H minus T delta S. So we use the equation delta S F S S FUS equal to delta H FUS over TF equal to 6.01 kilojoule per mole divided by 273 Kelvin equal to 0.0220 kilojoule per Kelvin point mole. The entropy change is positive as the solid state changed into the liquid state. If the transition went from the liquid to the solid state, the numerical value for delta S would be the same, but the sign would be reversed since we are going from a less order to more order situation. Next, a similar calculation can be performed for the evaporation vaporization of liquid to gas. In this case, we will use the molar heat of vaporization. This value will be 40.79 kilojoule per mole. And the delta S VAP will be would then be as follow. So delta S equal to 40.79 kilojoule divided by 373 Kelvin, and we get 0.1094 kilojoule per Kelvin point mole. So the value is positive. Again, reflecting the increasing is disorder going from liquid to vapor. Condensation from vapor to liquid will give a negative value for delta S. So next.
Assalamualaikum and hello, my name is Alif Ikram. So I am tasked to conclude our findings. Therefore, without wasting any time, in conclusion, we managed to examine a special class of idealized process called isentropic process. This process refers to a thermodynamic process that involves both a diabatic and reversible process. Okay, so there is no transfer of heat or mass across the boundary of the system, and it is also frictionless. The so-called idealized process is expedient in engineering as a model of and foundation to comparison for real processes. Additionally, we also get to develop the isentropy efficiencies for various steady flow devices, specifically regarding turbines through the calculation. Lastly, through the process of answering the questions that we have provided, we managed to obtain better understandings about our given topic. Therefore, we can say that it is not an overstatement that we managed to achieve all of our project objectives. Specifically, we managed to introduce and apply the entropy balance to various systems. Since our topic covers two parts, which is isentropy efficiencies of steady flow devices and entropy balance. So that's all from our group. Thank you.